Cell theory and magnification. In this video I will be discussing cell theory and showing you how to do a magnification calculation. The principles of the cell theory. 1. Living organisms are composed of cells. This indicates that anything that is not made from cells, like viruses, cannot be considered to be living. Cells are the smallest unit of life. And 3. All cells come from pre-existing cells. Louis Pasteur proved that bacterium could not be spontaneously generated, and from that he was able to conclude that cells cannot be made from non-living materials. Before this, there had been some question about whether cells could spontaneously generate, specifically the bacteria and fungi found on rotting food. There are some exceptions to cell theory. Fungi, for example, form long threads called hyphae, which are multinucleate but do not divide into separate cells. The skeletal muscle fibres are, just like the hyphae in fungi, also multinucleate and also don't divide into separate cells. Bone cells are interesting because they have a large matrix of extracellular material around them, and the mass of that is much greater than the cell itself. And then the mammalian erythrocytes, when mature, have no nucleus, and so all of these show exception to the cell theory. All living things need to be able to do the following 7 characteristics. I've arranged them as Mr. Graham to help you to remember them. So that's metabolism, reproduction, growth, respiration, excretion, homeostasis, and nutrition. All unicellular organisms can also do these 7 characteristics as shown by the amoeba. So an amoeba can metabolize their organic materials to sustain life. They're able to detect changes in their environment and respond to them. For example, here you can see that they have detected some possibly food and are responding to try and engulf it. Clearly they can grow and they can reproduce. They're able to excrete through exocytosis, and you can see vesicles moving towards the outer surfaces of the cells to be able to do that. They're able to control their internal environment. This is particularly important for an amoeba because they're waterborne, and so if the water content of the cell changed dramatically, that could result in a big problem. And they're able to absorb nutrients through endocytosis, as being shown here. It is worth remembering when considering cell size the importance of surface area to volume ratio. If a cell becomes too large, then the surface area to volume ratio will no longer be sufficient to enable all the components of the cell to diffuse into it, and at this point the cell will then divide. So that becomes a limiting factor to how large a cell can be. Now obviously most cells are sort of within this bracket in terms of size, and this just shows them relative to other familiar objects. It's important to have an understanding of units when we're doing work to do with magnification and cell size, and the standard units that we use all follow a scale in the thousands. So going from 1 metre to millimetres, if you were saying I've got 1 metre, how many millimetres would I have? Then you would times it by 1,000. And likewise, if you're going from millimetres to micrometres, and if we're going from micrometres to nanometres. The reverse is true, they're all 1,000s, but this time instead of multiplying we divide by 1,000. Now you will notice that centimetres aren't included in this because centimetres don't fit the 1,000 rule. The centimetres would fit in here, and they are 10 to the minus 2 metres. so they don't work in quite the same way, and consequently it's always a good idea to convert your units to millimetres rather than centimetres. When doing magnification calculations, you need to remember the equation, and the easiest way to remember it is simply to use this triangle I am. So I stands for image size, A stands for actual size, and M obviously stands for magnification. If you can remember I am, then you should then be able to rearrange this equation very, very easily. In this question, we're going to be asked to calculate the magnification, and we've been given, or will be given in a moment, an actual size for the length of this mitochondria. So the first step is to measure the image size. So we take our ruler and measure the length, which is coming out at 14.2 centimetres. So our actual size is 40 micrometers, and our image size is 14.2 centimeters. Now the first thing that we need to do is to convert the units of the image size. So I measured it in centimeters, but I'm going to change that straight away to millimeters. So that's 142 millimeters, and then we can convert that into micrometers, because we need to make sure that the image size and the actual size are the same unit. Now you could convert the actual size to micrometers. Personally, I prefer to do it the other way around because I find dealing with decimal points much more difficult than dealing with zeros. So this is now going to become 142,000 micrometers. We now need to put this into the equation. So we have our triangle here of I am, and we want magnification. So magnification is image size divided by actual size. So that is 142,000 divided by 40. And the answer that will give us of 142,000 divided by 40 will give us 3,550. Now, magnification doesn't have a unit as such, so you put a times there to indicate that that is your magnification.